Welcome to my mini presentation on my poster. My name is Julia Seidel. I'm a PhD student at the University of Geneva in my last year under the supervision of David Ehrenreich. And I just want to introduce you real quick to my poster on the atmospheric wind retrieval in the area of high resolution spectroscopy on the ultra-hot Jupiter WASP-76b. What you can see here on the left is a little bit of an introduction to high resolution spectroscopy. But more importantly, my results from my first paper that I published in 2019, where you can see here on the left the relative flux in the wavelength range of the sodium doublet for WASP-76b. And the most important feature is that the sodium doublet lines are very broad in comparison to the instrumental line spread function of the instrument, which was HARPS. What I did then is I used MERC, which is a multi-nested eta retrieval code that I wrote in 2019, which was published earlier this year, which combines nested sampling retrieval with wind broadening. So either a super rotational wind that rotates faster than the planet itself, or a jet stream from the day to the night side, or an upwards vertical wind that kind of pushes the atmosphere out. And here on the right side, you can see a little bit of an animation, what it means broadening-wise to have each of these wind patterns on the planet. And here below, you can see the first application of this code that was still quite rudimentary on the hot Jupiter HD189733b, a canonical one that we all know quite well. And a little bit of an artist impression that I made myself, where you can see the band structure that is already known from other theoretical work. And this outwards pushing cloud of sodium that I retrieved with the MERC code with wind speeds up to 40 kilometers per second. But this is just an upper limit for the wind speed. So I've spent the last year on upgrading this code, because before that, there were always constant winds that sometimes gave unphysical results. For example, jets crossing over the poles because everywhere the wind speed was the same. Obviously, that's not how the real atmosphere works. I did this in the first round of MERC like this because it's very computationally efficient. But now I spend the time to move to a 2.5D calculation of the atmosphere and introducing a cosine latitude dependence for some of the wind patterns to make it more physical. This also means that now we can retrieve wind patterns in the lower atmosphere of the planets because it's more sensitive to wind changes. And it also means that we're not talking about upper limits anymore, but we can actually restrain the wind speeds a little bit. And this is what I did for WASP-76b for now on HARPS data. And the results are actually kind of quite fascinating. Here in red, you see the best fit, which is a very good fit to the data. And it also converged quite nicely, as you can see here in the corner plot. And we've learned for WASP-76b that there is a day to night side wind in the lower atmosphere that's kind of in the same velocity range as was found in the Ehrenreich et al. 2020 Nature paper. So this is all quite encouraging, but obviously we need more than studies on 2 hot Jupiters to find out whether this is a general trend. So please contact me if you have further questions, and thank you for checking out my poster.